Hello, everyone. My name is Myungkoo Kang. I am a research scientist working with Professor Kathleen Richardson in the College of Optics and Photonics at the University of Central Florida. In this talk, I will be going through an exciting topic, which is how a combination of multi-component chalcogenide glass ceramic nanocomposite, post-thermal process, and 3D microstructural metrology method allows us to have gradient refractive index infrared media, which are alternative to flat optics. There's so many places where infrared systems are used as demonstrated by a few examples, such as sensors and lenses deployed in the military, industry, scientific research, and personal usage. The core component of many of those systems is lens, which refracts light. Meanwhile, electromagnetic waves with different wavelengths going through a lens naturally refract at different angles, which makes converging transmitted waves into a same focal point very challenging. This induces the chromatic aberration in a resulting image as shown by the blurry looking lady on the bottom. To solve the issue, additional corrective lenses with different shapes and refractive indices are typically inserted, as exemplified by the double Gauss lenses. However, multi-stack lens, typically made of high-density crystalline materials, inevitably makes it very challenging to minimize the size, weight, power consumption, and the cost factor of the entire imaging system. The fact that a challenge to minimize such factor comes predominantly from the lenses has required the modern optical community to rethink the strategy. Meanwhile, the nature has taught us what most efficient structures are in many cases. One of the most striking examples is lenses within eyes of living organisms. The microstructure of the human lens has spatially varying mass density, which corresponds to a gradient refractive index ranging from 1.36 to 1.44, as shown in the plot here. The green profile removes much of the chromatic aberration, thereby allowing the eye to image with good resolution. This technological evolution realized in a living organism has inspired the optics community, thereby giving birth to bio-inspired optics. This illustration on the right shows the proof of concept for the biomimetic single component green flat lens, where the propagating light is guided along the curved trajectories. The great advantage of the green lens include: first, it requires only a single component to correct the chromatic aberration. Second, it can have a aspherical, such as flat or even arbitrary shape. And third, it allows the optical platform with high design degree of freedom, thereby paving the way toward the previously uncharted novel optical functions. So the creation of green profile was pioneered by Dr. Robert Wood in 1905, where he dipped a cylinder in a chemical bath such that the fusion of external element induced the spatially varying refractive index within the cylinder. This preliminary technique has been substantially and systematically revisited and recreated in the form of flat green media by iconic Professor Duncan Moore, who is well known in the world by his participation as a chair of Hubble Telescope Independent Optical Review Panel to determine the correction prescription of the telescope in 1990. Since then, multiple other methods have been demonstrated to create green profile. Notable demonstrations include molding of multiple layers with different refractive indices realized by Dr. Jess Shanghara's group at a Naval Research Laboratory, and the formation of glass ceramic nanocomposite produced by Professor Kathleen Richardson's group at the UCF, where the volume fraction of high refractive index crystals is spatially induced, which is a key method used in my study in her research group. So the chalcogenide glasses are composed of a chalcogen element on the group 6, such as sulfur, selenium, or tellurium, which are then covalently bonded to other elements, such as lead or antimony or arsenic. These glasses, as shown in the spectra in the middle, have been demonstrated to have broadband transparency in the infrared, and hence have been major materials for infrared lenses. So a key question is, among these chalcogenide material, which one is susceptible to thermal treatment? and can be converted into green media. The ternary diagram you see on the bottom left is constructed for the bulk chalcogenide material made of germanium, arsenic, lead, and selenium, which undergo melting at high temperature and fast quenching down to room temperature. The entire area is largely divided by two regions, including glass forming region on the left and spontaneously crystallized region on the right within the diagram. Materials with composition located within the spontaneously crystallized region have crystal with large size distribution, making them basically not really ideal for optical material. Meanwhile, the glass forming region is what makes this material really interesting. Specifically, the temperature composition diagram on the bottom middle is constructed along the blue dotted line drawn within the glass forming region of the ternary diagram. Noticeably, there is a immiscibility dome over a wide range of composition where those outside the dome are expected to be morphologically homogeneous, while those within the dome are expected to be phase separated, as shown in the four examples on the bottom right. The two separated horizontal and vertical phase diagram you saw from the previous slide are now combined together to show their 3D phase diagram. Now let's look at the two cases where the percentage of lead selenide in the material system is either 20% or 40%, which are all located within the immiscibility dome. One of the two stars located on the left side within the dome means that the particles are lead rich and their matrix is lead deficient, while the one on the right in the dome would be inverse structure where the particles are lead deficient and the matrix would be lead rich. Since the lead rich regions have been experimentally demonstrated to be energetically unstable, external stimulation such as heat treatment can easily make them exclusively crystallized, while the lead deficient regions still remain glassy. We can clearly see those transition in these TEM images on the bottom, where the initially spear-shaped feature have asymmetric boundaries when the heat treated. And in the high resolution images, you can see one region is crystalline while the other region lacks of the crystalline fringes, which means glassy. So now, how do we know which one is lead rich and which one is lead deficient? The phase diagram already gives us the prediction, but we need experimental verification. The spatial segregation of lead is clearly evidenced by XEDS compositional map and atomic percentage profiles for the 20% sample, where the increase in lead composition happens within the particle. Let's then look closer what happens when these bulk glasses are heat treated. These XRD data on the top shows what type of crystalline phase is created within the bulk samples with change in composition from 0 to 40%. From the XRD spectrum, we then extracted the volume fractions of each crystalline phases for each composition, as you can see on the middle. Most importantly, lead selenide or germanium lead selenide crystals have refractive indexes close to 5, which is way higher than those of other crystalline phases or counterpart glass phases, all of which are below 3. So what does this mean? This means if we can systematically control the extent of crystallization of those lead-rich guys and maintain their nano size, then we can increase the effective refractive index of the entire nanocomposite while keeping their infrared transparency. An easy example of controlling the degree of crystallization is to increase the heat treatment temperature, which would increase the effective refractive index of the resulting glass ceramic nanocomposite due to the formation of the high refractive index crystalline phases. The 3D plot on the right correlate starting materials composition, heat treatment temperature, and resulting refractive index, which can serve as optical design toolbox, which allows us to know which composition and which heat treatment condition are needed to achieve the specific target refractive index. So the index modification process, such as heat treatment, we went through in the previous slide, are done in spatially homogeneous manner based on the process know-how we then came up with idea as to how those external stimulation could spatially change such that the index modification could be also done in spatially non-uniform way, which is basically gradient refractive index. For bulk material here, we use the gradient heat treatment to induce the linearly varying extent of crystallization of lead-rich particles and correspondingly a refractive index of the resulting glass ceramic nanocomposite. Specifically, a 50 millimeter long glassy rod with 20 more lead selenide underwent heat treatment within a gradient furnace. Here, the temperature extremes of those the rod spanned from 225 degrees C near the furnace cold end to 260 degrees C near its hot end. Then the resulting glass ceramic rod, upon gradient heat treatment, was cut into slices for microstructure and optical characterization. The two TM images collected from the slice 1 and 10 show that the asymmetric nature of the bright lead-rich secondary phases in its dark matrix of slice 10 is greater than that of slice 1, indicating that the slicing higher heat treatment has a higher volume fraction of lead-rich crystalline phases. The mid-wave infrared refractive index spectra collected from the slice 3, 6, 8, and 10 are shown here, and the value of effective refractive index monotonically increase as the extent of crystallization increase, confirming the creation of green medium. So our approach has been employed to employ a iterative optimization process from design to process parameter to material structure to resulting property, thereby getting closer to ideal maximum performance. Here, knowing a predictive quantitative relationship of these stages would really allow us to efficiently and accurately realize the properties required for the target device. And transmission electronscope has been key method to identify the structure of starting and processed material and connect the dots between the process and resulting property. A key question here is whether we really have accurate geometrical information such as size, volume fraction, and connectivity of those coexisting phases in nanocomposite, which would be one of the key input parameters going through optical design and calculation in iterative optimization process. Since cross-sectional TM specimens are thin slabs of thickness less than 50 nanometer to be electron transparent, the technique only provides nanocomposites microstructure from 2D perspective. Therefore, TM has an intrinsic limitation in identifying how secondary crystalline and glass matrix phase are distributed in 3D space. Understanding such a spatial distribution of the phase is critical in understanding the optical performance of the composite media, as it is impossible to model the optical functionality of device performance without the spatial distribution and variation of such microstructure. For nanocrystalline precipitate, smaller than the thickness of cross-sectional TM specimen, electron beam penetrate both the precipitate and the surrounding matrix, thereby collecting the integrated signal coming from the two phases. For precipitate larger than the thickness of the cross-sectional specimen, the precipitate seen in TM images are sliced views of the portion of that feature, omitting the key morphological information. These two situations are very briefly shown in the two illustrations on the top left. Also, XCDS and EARS provided by TM has atomic number dependent detection sensitivity. In the well-known plot of the minimum detection level, you can see why those with low atomic numbers would have to have large quantity to be barely detected, which means when you have low concentration of those such as boron or lithium, XCDS and EARS have intrinsic limitation. Furthermore, generally speaking, when a tool has higher detection sensitivity, the tool's spatial resolution is compromised, which means higher detection sensitivity shines when you look at the large area. Vice versa, when you look at a very small area, the detection sensitivity is often sacrificed. The resolution detection trade-off is illustrated here on the right. And you can see how TM has maximized the spatial resolution while sacrificing the detection sensitivity. In the case of solution process, where one of the multi-phase is left behind after chemical etching, the size of the remaining particle is not only changed, but also their interparticle spacing would be also changed due to the absence of the surrounding phases. So these issues really tell us we need an alternative metrology method which provides good detection sensitivity, good spatial resolution, and most importantly, all of these in 3D space. So this is where atom-proof tomography as a 3D tool can be introduced to fix this issue. Tomography utilized the multiple cross-sectional images collected from the target, which are then compiled back to the 3D structure of the target material. The technique allows the identification of distribution of the inclusion within their matrix, often not possible in projection methods such as TM, where those inclusions are seen overlapping. The atom-approved tomography, shortly APT, they utilize and exploit this concept at the nanoscale. In the technique, a pulsed laser beam is focused on the sharp tip of a specimen to promote field evaporation. Then the constituent atoms travel through a vacuum toward the detector, yielding a time of flight measurement, which is then used to determine their mass charge ratio, thereby identifying the type of element. This process is conducted repeatedly while a specimen is being mirrored away by the pulsed laser beam. This method allows a 3D reconstruction of the specimen structure created using a detector coordinate and ion sequence, as you can see in the example on the bottom. Over the past 2 decades, APT has gained tremendous interest due to its ever-growing applicability on a wide range of material systems. A distinct advantage of APT are that the technique provides both high spatial resolution, less than 1 nanometer, and also high detection sensitivity, around like 1 ppm, which are often the competing trade-off in other conventional micro-nano analysis. Such capability makes the analysis of the system such as ours very unique because the tool provides systematic mechanistic information not possible within the static information offered by TM. Furthermore, the technique has an equal sensitivity to all elements and provides isotopic information too. A key challenge is that the chalcogenide nanocomposite have multiple phases with very different evaporation fields. Phase within high evaporation rate leave a target material way faster than the other phases, such that the chunk of molecular cluster ions suddenly hit the detector, which have an impact on the electric field applied between the tip and detector. Not to mention that the shape of target specimen's tip become irregular, such that a laser-induced evaporation of the material becomes spatially uncontrollable. These things are reflected as a multiple burst in the voltage history on the top left plot. We know that laser pulse energy is basically a key quantity which dictates the speed of evaporation. So what we've done is that we gradually lower the laser pulse energy to alleviate the issue coming from different evaporation fields of multi-phases. The multiple voltage profile from top to bottom show we started from the very undesirable situation where you get tons of burst to a final point where we got rid of most of the burst. The improvement is clearly seen when you compare the voltage profile from our first experiment and the final one, as shown in the plot on the top right, indicating that with the optimized condition for such a nanocomposite, we can evaporate each phase at almost the same evaporation rate. Plus, as you can see on the bottom right, while we decrease the laser pulse energy to fix this issue, we were still able to keep the detection rate and number of ions collected very reasonable. With this almost like 6 months long optimization process, we were able to get a desirable mass spectrum at the detector with an outstanding mass resolving power greater than 1000, allowing clear assignment of each elemental and compound ions to observed peaks at each location of the detector, which are then converted into a map of elemental distribution. These are reconstructed three-dimensional iso concentration maps of the glass and glass ceramic nanocomposite with two representative compositions of 20 and 40% lead selenide. We can now clearly see how the coexisting phases are distributed, and very importantly, we can quantitatively see how the four constituent elements spatially change when we move from the one phase to the other phase in all cases. A key question here would be how the compositional and geometrical data provided by APT would be differentiated from those using TEM. Here shows the example of composition. Evidently, in the top middle figure, we can clearly see the difference in magnitude and trend of composition when we use APT or TEM. We use the compositional and geometrical information extracted from both tools and then inserted those factors into effective media approximation and scattering calculation to predict effective index, Abbe number, transmissive behaviors of the nanocomposite, where you can clearly see that those prediction using APT is a lot closer to experimental value as compared to those using TEM, demonstrating the usefulness and robustness of APT-assisted characterization. Okay, so the key takeaway in my talk is that our chalcogenide nanocomposite based upon germanium, arsenic, lead, and selenium have been proven to be a great candidate for the introduction of green profile using a thermal process, and index change can be systematically and spatially tuned. We are now entering into a three-dimensional microstructural methodology where we are striving to construct a really accurate predictive design process structure property relationship, which can be used for the glass scientist and optical designer to efficiently and accurately realize the target green devices. While the APT-driven material characterization and optical calculation provided us a really great result, there is still so much to improve. First, the sample prep based upon the conventional gallium ion FIP could potentially change the target specimen's microstructure, especially in the case of the radiation sensitive sample like ours. Meanwhile, the xenon plasma FIP system utilized the inert xenon gas as the milling agent, and the chemically inert xenon gas at an ultra low temperature has a very low reactivity with the vast majority of the element, and is expected to minimize the undesirable secondary ion matter interaction within target material, which are sensitive to other types of ion. APT provides three-dimensional microstructural information, but when it comes to the ability to capture the microstructural evolution on live, in situ TEM can overcome the static information from APT and provide time-dependent information over the range of temperature. So I think the combination of these two methods could provide us space plus time information, namely fold information, which then could be inserted into optical computation tool where we can have the more accurate predictive platform, the correlating the process to structure the properties, which would really benefit the development of the optical material. So lastly, I'd like to express many thanks to those who have been contributing to this study. And with that, I welcome your question. Thank you very much.